Hi, my name is Eric Jamois. Thank you for joining me in this ADMET Predictor interactive tutorial dedicated to MedChem Studio. For reference, I'm using version 10.2 of ADMET Predictor, also known as APX.2, which at the time of this recording is the most recent release of the software. So our topics for today will focus on clustering, R-group analysis, and activity or cliff detection, also known as matched molecular pair analysis. These functionalities are an essential part of the capabilities in MedChem Studio. There's actually a lot to cover in this tutorial, so it may run a little bit longer than the other one in the series. As a quick sidebar, MedChem Studio used to be a pay-for module, not to be confused with MedChem Designer, which has been free for a very long time and still is. So starting in September of 2021, with the advent of the ADMET Predictor 10.3 release, which will also be known as APX.3, MedChem Studio will also be free. However, you will still need a license in order to access these capabilities. Make sure you reach out to a licensing department to request your free license at licensing@simulations-plus.com. So without further ado, we're going to get started, and we're going to work with a data set which was shared with us by Edelris, which is a company involved in very interesting natural product topological mimetics. So I'm going to open a file of 500 peridooxyzipinones, which again was kindly shared with us. And in this instance, the identifiers for the compounds are stored in a field labeled EDX. So we're going to specify the name of that field in order to import our compounds. And as is often the case in ADMET Predictor, we are going to proceed to calculate ADMET properties for these compounds. And so under Data, Calculate ADMET Properties, we're going to proceed and calculate all ADMET properties for these 500 compounds. And as you know, ADMET Predictor is very quick, so it's just going to take really a couple seconds before we get these properties back to us. So the first thing we need to make sure is that the MedChem Studio functionality is actually enabled, which is called here the MedChem features. If so, just go under View and look for MedChem features. If you have a check mark in front of it, you should see 5 tabs at the bottom of the spreadsheet labeled Compounds, Classes, R tables, Pairs, and Keys. If it's disabled, then you would really only see the Compounds tab. So we're going to go here and activate these capabilities. So what we're going to do now is actually we're going to cluster this set of compounds into chemical families known as chemotypes. And you can do this very easily in ADMET Predictor. The first thing I'd like to do, though, is just to show you that under this Classes tab right now, what we have is really, we have each compound in a class of its own. So we actually have as many classes as we have compounds. So we have 500 compounds in the Compounds tab, but we also have 500 classes in the Classes tab. So let's go back to our compounds here. And the way you access the clustering capabilities is under Chemistry. Just go to Generate Classes. Okay, and the default is to use frameworks. However, in this particular instance, our compounds really have been assembled from core and R groups, and therefore the ring anchored systems is actually a more appropriate option for them. Actually, we have a few cores, highly related cores, that have been used as the basis to assemble these 500 compounds. So again, we're going to choose ring anchored systems here because they were really fundamentally assembled as a co-1R group kind of system. So we'll use that option. And what the software does, it'll do a few things. So the first thing is that in the compounds tab, it's going to create a class list column which contains the class ID for each compound, or cluster ID. I'm going to use cluster and class really in an interchangeable way here. So each compound is assigned a class or cluster ID, like compound 1 is assigned to cluster 2, compound 2 is in cluster 1, so is compound 3, etc. And it also gives you the size of the cluster. So that's the number in parentheses here. So cluster 1 contains 299 compounds, cluster 2 contains 132, etc. Now we can have a little bit more of a detailed view of what's going on by going to our classes tab here. And what we see is that now the chemotypes have been assembled, in this case, as four different chemotypes. And what we see is that in classes 1 and 4, we have what we could call regular pyridoxyzipinones, and in classes 2 and 3, we have the sulfonamide analogs here. The other thing that we see is that, so we've identified our 4 classes, and the software has also output for us each class or cluster size. Cluster 1 has 299 molecules, cluster 2 has 132 molecules, cluster 3 has 59, and cluster 4 has 10. Okay, so the other thing that we see is that the software has really defined these classes pretty much the same way that a chemist would have done it, in the sense that one would probably have put the regular pyridoxyzipinones together initially, and then maybe split them in 2 separate classes depending on the regiochemistry of the pyridine ring. So notice that we have 2 different regioisomers here, with the nitrogen being either placed here or here. And then probably initially it would have defined a second class of the sulfonamide analogs, and likewise it would have made a dichotomy based on the regiochemistry of the pyridine ring, with similar differences between these two classes. So I think what we have here is a pretty accurate reproduction of what would have been done sort of intuitively, separating those chemotypes, those chemical families. So one thing that's interesting here is that we can look at this data set at different levels. We can look at the data set at the compound level, where for every single compound we can look at properties that are associated with these compounds. That's the columns, of course, that we have here, and they can be either just plain numbers, but they can also be star plots, which are these depictions. Okay. So again, we can look at the data at the individual compound level, but we can also look at the data now at the class level, which gives us a very good insight into potential assets and liabilities associated with these chemical families. So, and now, if we look at the data in the columns, it really no longer reflects an individual compound. these values, such as this ADMET risk column now, is actually the class average across the chemotype. So 1.487 is really the average ADMET risk across cluster number 1. Okay, and the other thing that we can do is now, rather than looking at individual values, although that gives us a pretty good insight on average, which class is performing better, but we can also look at the star plots. So, for example, if we look at the CYP substrate specificity, we see that the quote-unquote regular pyridoxazepinones are predicted to be rather promiscuous against the CYP enzymes, meaning that they are predicted to be metabolized by a pretty large panel of the CYPs. Whereas if we go to classes 2 and 3, which are the sulfonamide analogs, then these are predicted to be metabolized primarily by the 3A4 isozyme. So that's kind of a notable observation, again, between these classes. The third kind of information that we can look at is actually property histograms. And there is one that is generated automatically for us, which is the molecular weight information across each class. We can actually create more of these histograms, which again will give us more insight into the distribution of properties for each one of these chemotypes. So for example, if we go into the header here and right mouse click, then we can go and into insert column, and at this point select graphical distribution. Okay, so if we select this, then we have the ability to choose between the entire set of properties that we've calculated on our compounds, and for example, we can choose ADMET risk, and the software will add a histogram distribution. So again, we can see the distribution within each one of these clusters. And let's say we decide to do the same for, say, Herc filter. So we're going to insert a column and a graphical distribution. And if we go down on list to Herg, which is alphabetical, and this is Herc filter, and that's a categorical model, which is yes, no, whether the compound is predicted to have any kind of liability for Herg. If it's 0, it's no, and if it's 1, then it's yes. So we can add this. And what we see again is, it's an interesting way to look at the data set at a somewhat higher level. And we see that for example, ADMET risk, for classes 1 and 4, the compounds are distributed with a higher proportion of compounds on the lower end of ADMET risk, but still trailing towards potentially higher values, especially for class 4, although it's a relatively small class. On the other hand, if we look at classes 2 and 3, we see that there is a much stronger focus on compounds that have low ADMET risk and considerably less compounds in the sort of trailing end of the distribution. And likewise, if we look at Herg, we see that for class 1, it's predicted to be almost even between compounds that are predicted to have no Herg liabilities and compounds that are predicted to have a potential Herg liability. So again, in class 4, there's a slight bias towards compounds with lower Herg liabilities, but there's still a fair number of compounds in the other bin. On the other hand, if we look at the sulfonamide analogs, we'll see that there is actually a much larger bias on the compounds which have lower liabilities towards Herg rather than those that are predicted as potential problems. So again, this is the kind of information that allows us to potentially balance the number of compounds we'd want to make in each class. And as I mentioned earlier, sort of assign assets and liabilities to each one of these classes. So as the next step, I wanted to show you really how you can do a few more things with these compounds. And the way that they look right now is, as you can see, these scaffolds are not really aligned with each other, which kind of makes looking at them and comparing them in terms of, regiochemistry and other aspects a little bit more complicated. So I wanted to show you how you can align compounds using a combination actually of MedChem Studio and MedChem Designer. So what we're going to do here is take these 4 classes of compounds into MedChem Designer. And the way you would do that is just by going to this MedChem Designer icon, which is this aldehyde depiction, aldehyde icon over here. So by pressing this, you actually get your 4 compounds into a MedChem Designer window. And the first thing we'll do is to put the first compound in an orientation that we like. So what you would do is just basically lasso this compound and right mouse click and clean up. Okay, and that's going to put the compound in a preferred orientation. But of course, you can tune it to your preferred orientation. In this particular case, I may want to flip this compound vertically if I want to see the carbonyl up, for example. So, and then if we select all of these compounds, you can do this by selecting Control A. That will select all compounds. That's the select all function. And then you can align all of these compounds by common scaffold. Okay, and then it's just going to become a lot easier to look at them, and then we can send them back to our classes tab. Okay, so we're just going to transfer them. It says 4 compounds will be transferred, and they are existing compounds. There's nothing new here that we would have modified. So we'll just say OK. So the software gives us a warning message that at least one structure has been modified, and that the ADMET properties that have been calculated may be out of sync with the structures. So however, here we really haven't modified these structures. We've really changed their orientation. So none of this is going to have any effect on the calculated properties. So we can just say no. Okay. All right. So now it becomes a lot easier when we go to our classes tab to actually compare these chemotypes and these regiochemical differences that I was pointing to before between classes 1 and 4 and 2 and 3 become a lot easier to see. Okay. So now we've aligned these scaffolds with each other. Notice that if we go to the Compounds tab, all compounds are still not aligned with each other. They are really in whatever orientation they were when they were entered or drawn in by the chemist who put them in. And of course, it would be a lot easier to look at these compounds if the scaffolds were in the same orientation. And there's actually a very easy way to do this. Very simply, what we can do is go to our classes tab and then hit this Compounds tab over here and propagate that alignment sort of back to the compounds. Okay. And this will actually do 2 things. It will align the compounds to each other, and it will also highlight the scaffold in blue, whereas the R groups will be in black. So again, that makes looking at the core and R group motif a lot easier than in the previous way that we had them drawn. So This kind of alignment is actually something you can do pretty easily in MedChem Designer alone. However, you would have a limit of 100 compounds. Okay. So as you can see here, you have a core and R group motif. The logical next step is to say, well, I really would like to see a core and R group decomposition for these molecules the way that it was that these compound series were initially designed. And again, that is something you can do very easily. Just simply highlight class 1, for example, or any of the classes, and select the R tables tab at the bottom here. And that will actually trigger the core and R group decomposition for these molecules. And the other thing that you can do is in the R group analyzer actually display properties alongside each compound. So you can see here, you can look individually at each R group. For example, for R group 1, you can see if you have just a hydrogen atom as the substituent, what the distribution of properties, of certain properties, is going to be for the other R group combinations with R1. And you can do the same thing with the methyl group. You can do the same thing for each R group, which is very convenient, but you can also do it in combination. Okay, and now you can project, of course, any property that you've previously calculated onto these plots. So for example, if we want to take a look at our composite function of ADMET risk, then simply select ADMET risk, and that you can see that for certain R group combination, for example here for R1 equals hydrogen and R2 equals benzyl, that maps to 5 compounds, 4 which have low ADMET risk values and 1 which has a high ADMET risk value of about 4.9. Now if we look at, say, methyl for R1 and the same benzyl group for R2, then we would have 3 compounds, 2 of which have low ADMET risk values and 1 which has a high value. Notice we don't have the same number here because we have a sparse matrix. Actually, we only have 299 compounds. We will see later that, of course, this maps to a larger superset. Okay, so again, that's a very convenient way to analyze these R group combinations, and you can do this for any combination of R groups, R1, R2, R1, R3, etc. If you want to take the ones that have the largest numbers like R2, R4, then you just select this, and then you can see how the mapped property, which in this case is ADMET risk, would be on the individual resulting compounds, which in this case is mostly 1 or 2, depending on the R1, R3 combination. So in this way, you can sort of assess, certain assets and liabilities to these R groups. And again, we're only looking at ADMET risk here. You could do this for any property that you'd like to investigate, solubility, or pretty much anything else that you can calculate or import within the software. So one of the things which I'd like to close with is the fact that we really have a matrix of R groups, which in this particular instance map to 299 compounds, which was our class 1, and these are the exemplified compounds. Okay, and that was drawn from a larger superset, because if you look at the full matrix, which is a 2 by 13 by 4 by 25, that is a matrix of, well, 4 times 25 is 100, by 13 is 1300, by 2 is 2600. So we have a full matrix of 2,600 potential products, which could potentially be made, of course, assuming that there is no conflict between the introduction of R groups within the chemistry that is being used to assemble these compounds. But what we can do is we can actually enumerate this full library of 2,600 compounds of the superset, if you would like, which could potentially be made. So we're going to do that right now, and it's very easy. Under the R tables pull down, you can select this explode products option. Simply specify the output file name. So for example, we are going to be taking compounds from class 1, so we can call it class 1 underscore full, because that's the full set of compounds, and 2600 because we're going to get 2600 in this case. Okay, and then we really don't need to display them in a new window. We just want to enumerate them to a file. So just press OK, and the software will actually explode or enumerate this full set of products to an SDF file. So again, there's a lot of things you can do here. This is only the first part of this tutorial. I'd like to see you in part 2 on the other side of this and show you the kind of analysis that you can do on this exploded set. So thank you for your time. We'll be right back. Okay, so welcome back. We're going to go through a few practical examples on how to evaluate the profile of a compound subset, and also how to select one in the first place. And then we will move on to the last section of this MedChem Studio tutorial dealing with matched molecular pair analysis. So let's restart where we left off, and so we're going to read this set of 2,600 compounds that we just exported, which were our exploded products from class 1. So we can read these compounds in now, and I'd like to draw your attention to the fact that the compounds that were part of the 299 exemplified subset have an identifier starting with EDX in the product in class column, whereas the compounds that have remained virtual and were not exemplified do not have any entry in this column. And that's going to become important for some of the analysis work that we're going to perform next. So the first thing we're going to do is to calculate ADMET properties for these compounds. So let's just go ahead and calculate properties like we've done before. Again, ADMET Predictor is very fast. This is a multi-threaded calculation. I'm running on a standard laptop here, and I've set it to run on 7 threads. So again, it proceeds really quickly. And well, here we go. We're already done. So the results are back. So one of the things I'd like to show you is the distribution of properties for the exemplified subset, and these are compounds that were actually made. So if we take a property, for example, like solubility, or predicted solubility in this case, we have to look for S plus SW. So let's go ahead and look for our native solubility model. And we're going to actually use a log space here to do our display. So this is the distribution for the entire set of 2,600 compounds. Now, if we want to see just the compounds that were exemplified, the 299 that were exemplified, we can simply use the search function. So this is found under Edit, define text or Control F as a keyboard shortcut like you would do in Word or Excel. Just do Control F and search this product in class column. So this is the search attribute, would be product in class. You can really search for anything, but we're only searching this column for EDX. And just go ahead and do this. And that will select all of the compounds that have an EDX, well, an identifier entry in the product in class column. And then select the update chart, okay, at the top of, in the header of chart 1. And this will give you the overlay of the distributions between the selected compounds, that's the exemplified set, and the compounds that remain virtual. And what you can see is that there is a rather strong bias in the exemplified subset for compounds that have higher solubility or higher predicted solubility in this case, which is exactly what you want. Also notice that you have two different axes, two different y-axes in this particular chart. On the right, this is the scale for the selected compounds, the 299, and on the left-hand side, the other y-axis is for the unselected compounds. And you can do this kind of plot for any of the properties. Say, for example, you want to see a similar distribution, say for ADMET risk, simply go and select ADMET risk as your property. In this case, you would unselect the log scale and display this. And again, you see that the subset that was selected for exemplification is significantly biased towards compounds that have a lower predicted ADMET risk. So as you can see, there's a lot of work that has gone into the design of this subset. And what I'd like to show you next is how you would go about selecting a subset of your own. So this is pretty easily done. The first thing we have to do is actually go to chemistry and go back to what we've used before, which is our generate classes option. Okay. And what we've done before is really clustering, but now we know we're dealing with a single cluster. All of these compounds really came from our previous class 1. So all of these compounds are really a single cluster. So in this particular case, we're going to select single superclass as our option to generate classes. Okay. And you will soon see why we're doing this. And now if we go to classes, of course, we only have one class. And at this point, you need to define what's going to be used as the scaffold in order to divide the compounds, or to analyze the compounds in terms of core and R group representation. And the way you do this now is with your right mouse click, go to scaffolds, and you can define your scaffold using maximum common substructure. So go ahead and do this. You can leave the defaults the way they are and select this. And now this is our scaffold. So I'd like to draw your attention to something a little bit more advanced, that if you're dealing, say you have a scaffold and you have an ethyl group and say a propyl group, and if you use this MCS approach, maximum common substructure approach, to identify your core, it will probably identify the extended scaffold with the ethyl group as the core, and then just have a hydrogen and methyl substituent instead of the ethyl propyl, which is the way that you really want it done. So if you get into that kind of situation, you can actually edit the score by hand. So similarly, under scaffold, you can refine or modify the definition of your core using a lasso technique. So for example, here, if we decided that instead of this entire set of compounds being the core, we actually only want this to be the core. So you could do this as well. So again, you can do some manual touch-up on the way that the scaffold was identified. So we're just going to cancel here and leave it the way that it is. So at this point, we can go to our R tables because we've defined our core, and the software will again give you the breakdown of our 2600 molecules in terms of core and R group. And at this point, you can actually proceed to the selection of a subset. So in order to do so, under R tables, you will find this option, Find Subset Using R Groups. So you can select this. Under Find Best Subsets, you can define which property you want to use to define your subset. So maybe you want to optimize against solubility or against ADMET risk, which actually contains multiple properties. So for example, if we want to use ADMET risk, we will use 1 unconstrained R groups, 3 minimum number of unconstrained R positions as 1, maximum number as 3, we have a total of 4, and the number of compounds in each subset, in this case 100 is pretty good, and this is the number of solutions that the software will output, the maximum number of subsets to identify, maximum number of solutions. Notice that for ADMET risk, the lower value is desired. So we're going to leave this larger attribute values or better option unchecked. If you were dealing with something like solubility, you would actually want a higher value, so you would turn this on. Okay. So we're going to use this and say OK. And the software will actually identify, it will show you the R group combination that results in the optimized subset, and you can directly see on chart 1 here the distribution of ADMET risk compared to the unselected compounds. So we have 100 compounds, which was the target number to select, and 2,500 compounds that are unselected out of the 2,600. And you can see there's a very strong bias towards compounds with low ADMET risk in our subset compared to what remains unselected. Okay, and using this arrow here, you can basically advance towards the multiple solutions that were output as part of this selection process. And notice that our graphs are updated in real time to show you what the distribution of properties looks like. Okay, so that concludes that part of this library design work. We're going to switch gears now, and I would like to show you a few things about matched molecular pair analysis, which is also known as activity or property cliff detection. And I say activity or property because usually this kind of analysis is performed on activity, and again, it's often called activity cliff detection. However, this is something that you can do on any property that you can import or calculate within the software. So in order to do this, we're going to load a different subset. We're going to load this set of enamine compounds from their discovery set. Okay. And as we've seen before, the first step in performing this kind of work is to calculate properties. So we're going to do this, calculate ADMET properties, and just go ahead and calculate. And we have 2,000 compounds here, so it's going to proceed rather quickly. And we don't have activity data here, so we're just going to use properties for the sake of the exercise. And what we're going to investigate is what chemical changes result in the most dramatic changes in that predicted property that we select. So the first step is under chemistry. Here you will find the option to generate pairs. Okay. And there are a number of options, but the most important one is on which property do you want to do this? So for example, you could select an activity column, or in this case, we're just going to use our native solubility. Okay. So if you're happy with your parameters, just click OK. And this calculation is also multi-threaded. So we're using our 7 threads, so it's going to proceed really quickly. And the results are going to be found in our pairs tab over here. So if you select this, you will see which changes in chemistry, relatively small changes, result in potentially large changes in the target property that you are investigating. So here you're going from a thiolane to a pyrrolidine, and you can see the somewhat dramatic change in solubility from turning one into the other. Likewise, going from a thiophene to a furan here, we also have a pretty significant change, or from a cyclobutane to a methyl ether, we also have a pretty significant change. And of course, you can sort these changes by magnitude. So by simply clicking on the top here, you can sort them from small to large or large to small, which is what we have now. So again, the software provides you with a very easy way to investigate how dramatic certain changes, again, in activity or property can be, depending on relatively small chemical changes. So again, I hope this was useful. It concludes this tutorial. Thank you for your time, and have a wonderful day.